So anyway, so I'm going to talk about data models for supervised classification, and then I'm going to talk about algorithmic models for supervised classification. So, okay. So the simple one, so suppose you've got a binary outcome, and I've been talking about malignant and benign tumors, so I'm going to stick with that example. You're trying to predict if a tumor is malignant, and this is from a Wisconsin medical school breast cancer survey, not survey, that's kind of a weird word, study. And what they did was they had doctors investigate these tumors, and they ranked them from 1 all the way up to 10 on a whole bunch of different variables. Now this one that I have plotted here is thickness. They also looked at cell size, cell growth, how abnormal it is, like is it a pretty uniform blob or is it really amorphous? And so obviously these numbers really aren't super meaningful, other than this is bad, or this is super thickness and this is not super thickness at all. So I think they had a lot of patients and they needed just some way to classify it rather than take really expensive measurements. That's a lot easier for the doctor to look and say, oh, this is about a 6 as far as thickness goes. So in this situation, we've got, I'm going to classify benign tumors as y equals 0 and malignant tumors as y equals 1. So something that you could do, a simple idea, is to just run a straight line through them. So here's all my observations here, and they're plotted on top of each other. So I made the transparency a little bit lighter. So like there was only a few observations there. There was some here. There was a lot over here. Same thing over here. We've got a lot more observations that are in the I don't know, 6, 7, 8, 9, or 10 for the malignant tumors compared to the 0, 1, 2, 3, 4, 5, maybe 6 in the benign tumors. And so you can just draw a straight line, and you're basically modeling the probability that you would land into, or you have a malignant tumor or a benign tumor based on the thickness here. So around, if you've got a thickness that they recorded as 6, you would guess you've got like a 50% chance of having a malignant tumor or a 50% chance of having a benign tumor. Now, this is the quick and dirty, hey, once I learn regression, everything looks like a linear problem method to solve it. But it's by no means ideal, because this problem actually turned out pretty nice. But you could imagine another situation where there's like a lot of points here and a lot of points here, and then when you draw the line, this blue line is dipping below 0 and it's dipping above 1. So then it's predicting probabilities that are greater than 1 and probabilities that are less than 0. And you could just interpret that as being just, oh, I'll just cut it off at 1 and cut off at 0. But this is just really not the right tool for the job. You're in the right ballpark, but you can do better. And so the pros and cons of this method: your mother still loves you if you run regression on binary data, but that's probably the only pro of running it. The cons are that you're predicting probabilities that are less than 0 and greater than 1. And then we got lucky here because the binary response is just 0 and 1. But if you had 3 groups, do you code them as 1, 2, 3? I mean, maybe if they're ordinal, that might work. But even if they are ordinal, like, does it really make sense that, you know, the difference from the group 1 to group 2 is the same as the difference between group 2 and group 3? And if they're not ordinal, like eye color, I mean, obviously blue eyes are the best, but, you know, I don't want to rank them and bias my data in any way. So, I mean, how would you even do that? It's just, we can do better than simple OLS regression. And so along our knight in shining armor is logistic regression. And so the solution here is, let's not model the probabilities linearly, because we're going to get probabilities that are greater than 1 and less than 0, and that doesn't make any sense. So instead, you can use a function that's trapped between 0 and 1. It lives between 0 and 1, and it's not going to go outside of it. And such a function, a really nicely behaved function, is called the logistic function, which is this function right here. So we could model the probabilities as our logistic function here, which is just a function of our data multiplied times our different parameter values. And then what we get is, if we do the appropriate math, we get that this here, which is the log odds or the logit of the probability, that is now a linear model. So now we're back in linear land, we're happy, we can do our normal line stuff that we just love to do. But we're guaranteed that when we if I model this linearly, then I'm guaranteed that when I'm actually look back at what my predicted probabilities are, I'm okay. I'm still between 0 and 1, and everything's nice. And so yeah, this is called the logistic function because this is called the logistic regression because this is the logistic function. And that is called the logit. And the logit is linear in X, so this is a linear classifier. And so if I run logistic regression on my same cancer data, we get this nice curve, but it doesn't skirt below 0, it doesn't skirt below 1. And then I can say here something like, okay, if somebody has a tumor thickness of 6, I would go up here and I'd say, oh, there's about, about 60% probability that it's a malignant tumor. And then you could make some sort of cutoff. Like, you don't want to tell somebody, hey, I'm pretty sure your tumor is benign, if you don't actually you don't want to, scare the living crap out of them by telling everyone that all their tumors are malignant just so you're safe. But at the same time, you can draw some sort of cutoff here that I'm not going to tell somebody their tumor is malignant or not. Like 50-50 might be kind of dicey, but there's a 50-50 chance that it's going to kill you, right? That's not what you want to say. So the cool thing about these methods is you get some sort of probability statement on what group you belong to. So if you've got a tumor thickness of, say, 3, then it's really, really, really low chance that you're anywhere near being malignant. You're most likely benign. But if you need to do some sort of, cutoff, you can adjust on here and be like, oh, if I tell somebody that their tumor is benign, I really want to be sure that their tumor is benign. So you don't just get straight up predictions like, hey, it's benign or malignant. You get some sort of probability spectrum where you can say with some sort of certainty what probability their tumor is dangerous or not. So, the benefits of using logistic regression here is that it's a familiar framework. It's regression. We just have to tinker with it a little bit, and then we get back into what we've always done. And the cool part here, which I haven't really talked about the details too much, is you can get parameter estimates, and then, like I was saying, you could say that, okay, in this data set, thickness is just one of many possible variables. Then you could say, oh, thickness and such other variables are the best predictors of tumor type. And so if you're stretched for time or strapped for cash, let's check thickness and then these 3 other variables rather than a whole suite of possible variables. So you can pinpoint which ones probably are the best predictors. And the cons of logistic regression is this example we've seen here. I've got a binary response. It's perfect. It makes a lot of sense. For k greater than 2, so I've got more than 2 clusters, there are extensions, and it's called multinomial logistic regression, but they're not widely used to the point that the elements of statistical learning and an introduction to statistical learning basically say, oh, there's extensions, but nobody uses them. In this supervised learning textbook, they don't even really go into the details of it very much, mostly because if you've got k greater than 2, people tend to use linear discriminant analysis, which is kind of the other technique here. So the big thing that we have here is in logistic regression, we model the probability that y falls into some category based on the data we observe. We model that directly in logistic regression via the logistic function. In linear discriminant analysis, we kind of turn the problem on its head, and instead we model how the data are distributed given that you're in a particular class. And then thankfully we've got Bayes' theorem, and so we can just jump back to our normal prediction of what's the probability that that our observation falls into some category given whatever data we observe. So here we're going to be modeling this probability and then transforming back to get modeled probabilities for the probability that our response falls into some category. And the 2 assumptions that we have to put on the data here, or not, we don't have to, but this is what you do in linear discriminant analysis, is you assume that your X, your data matrix there, it's a p-dimensional Gaussian distribution with some mean mu k, so that can vary across the different classes, and some covariance matrix, capital sigma sub k. And the other simplifying assumption is that sigma sub k is the same across every single class. So basically the variance and covariance within some particular class is going to behave the same no matter what class you're looking at. And so obviously that may or may not be a realistic assumption, but if that's not a realistic assumption, you've got a whole bunch more parameters that you need to estimate, because for every single class, you've got a whole variance matrix that you need to estimate. Rather, in this method, across all the classes, you've got the variance of the different predictors and their covariances with one another. So if you actually are not happy with this assumption right here, and you do treat sigma sub k as different across the different classes, that yields quadratic discriminant analysis, which I'm not going to talk about here, but that's how you get there. That's the only difference, is that it drops this assumption. And then you can draw nice nonlinear decision boundaries. So the class density here, I mean, we've seen multivariate normal before. It's just this behavior. And so if I want to look at, well, which one's more likely that my response falls into, well, the probability that y is is in k, given that we've observed some data, over the probability that y is in some class, different class L, this is just going to be, so we call this the log ratio. And you get a lot of terms that cancel out based on your assumption that the variance matrices are the same, which leads to, if you look at the form of this function right here, it's linear in x, which is why we're getting the linear discriminant analysis. Now, if I had not assumed that sigma sub k was the same across all the different sigmas, then this term would not have canceled out when I take that ratio, in which case my new resulting function is going to be quadratic in x, which is then quadratic discriminant analysis. So if this ratio is positive, then x is more likely to have arisen from class k than class L. So I can look at this across all the different classes. It turns out if you do some nice algebra, really all you're looking for is that given some x, I want to find the k that maximizes this statement. And that's going to be the group that I classify this observation into. So for some observation with vector x, I want to find the k that maximizes this, and that's going to be where I place it. So for example, this is an example of, this is straight from, I can't remember if this is ESL or ISL, it's one of the two. And so what we have here is, here are the data. They are, there's some, we've only p equals 2 here. So we've got one variable here, one variable here. And we notice that the groups are multivariate normal. And so they all have the same variance covariance matrix, which makes, that's why the ellipses are not, one's like super oblong and one's circular. They've got the same variance covariance matrix, so they're going to look like the same ellipses. So this is what the data might be generated from, and this is maybe an example of the actual data. So ideally, we would want to classify on those dashed lines, because that's the best we could possibly hope to do, because there's some overlap here, but we're splitting it exactly the best way possible. But when we estimate different parameters in our model and run linear discriminant analysis, we would be in a situation where we're getting those dark lines there, we're getting the solid lines. So the linear discriminant analysis is approximating what they call the optimal Bayes decision boundary, in which case, ideally, we would want the dashed lines because that's going to give us the lowest possible misclassification. So that's what linear discriminant analysis is trying to tease out and get at. Now, obviously, some pros of this is that it handles multiple classes, which is not something that we were getting with logistic regression. And I'm not going to go into this too much, but the fact that we can put priors on the size of the different classes makes the whole procedure a little bit more stable. I was reading that like if logistic regression has well-separated classes and then the group sizes are a little different, that sometimes you get really unstable estimates, in which case it's kind of a giant pain. And so linear discriminant analysis, by introducing some prior information because you're in a Bayesian framework, helps out with that a little bit. However, problem, I make a huge assumption that the data are Gaussian, and I also make another huge assumption that the covariance matrices are the same. So if those aren't valid, maybe this isn't the right procedure to work on. So in continuing with my Dr. Seuss theme, I got a data set on spam, and I called it green eggs and spam. And what we're trying to do here is based on a whole bunch of different variables, classify my email as whether or not it's spam or not spam. And I didn't name the variables here because there's a ton of them. There's like 58 or something like that, 57 possible variables. And basically what they are, it's this data set from 1999. So I don't know how much email has changed since 1999 as far as word frequency and spam use goes. But it looks at some of the variables are the frequency of words that are, they look at the different word frequency in an email. So when they use the word make or address or all or 3D apparently, hour, over, remove, internet. This guy who got this data set, his name's George, so we had another one, that word freak George, the frequency of words that were George in the email. So he's trying to just look at the actual content of the email and classify whether or not it's spam or not. So I make a quick test set and training set. I'm not going to do 5-fold cross-validation or 10-fold cross-validation just because I'm just illustrating what's going on here. But this is how you might fit it in logistic regression. So afterward, if you're looking for a logistic regression problem, this code is going to be available online. So hopefully you can just put in your data and run it. But here, for example, 1 is spam and 0 is not spam. So if I run logistic regression on this, it's binary classification. I'm classifying 538 non-spam emails correctly as non-spam. I'm classifying 365 spam emails correctly as spam. And I mess up a few different emails. So eventually my classification rate here is about 93%, which is, I would say, pretty good. And linear discriminant analysis behaves similarly. It's a little bit worse, but again, that could be the training set, or a lot of what I was reading was that linear discriminant analysis and logistic regression perform very similarly in a lot of parts. And oftentimes computation isn't a super big deal. So most of the time people just say run both of them and see which one's better. That's really the best advice that I was getting on whether or not you should choose logistic regression or linear discriminant analysis. But mostly, I mean, some major other guiding principles are that logistic regression, if the response is binary, it makes a lot of sense to do logistic regression just because you can get some nice plots and you can make inference on the parameters, fairly straightforward. But with the Gaussian assumption, if that's not valid, then that's probably a really good place to use logistic regression. Similarly, if your response is not binary, you've got multiple classes, then that's when people tend to use LDA. So these are really the two data models that people use. I talked about quadratic discriminant analysis, and there's other extensions of these models, but these are the two primary players in the data modeling world. And this is probably the world that we're most comfortable in as statisticians.